డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయం విద్యార్థులకు స్వాగతం. ఈ ప్రసారంలో
Hello students, we are going to have a lesson on Zeeman effect, and this Zeeman effect is there in your MSc final year, both theory as well as practicals. If you see the monitor, you will see the photograph of Zeeman. Zeeman effect has been discovered in 1896. This is the arrangement for taking spectra of elements. The spectra of elements is taken from the light that you are seeing here. That light is sodium light. Like that, you can have in this bulb, if you put some amount of hydrogen instead of sodium, it will produce a hydrogen spectrum. In this particular case, we will see the sodium light is falling onto a spectrometer. This spectrometer consists of a collimator, a prism table and a telescope. There is something called a grating. This grating is of 15,000 lines per inch type. The resolution of this grating is high. So, if you want to see the spectrum of sodium, the grating should be kept on this and light must fall on the grating, it will come into the telescope, and as the telescope is made to move on either side of this, we will find the spectrum. The spectrum consists of D1 and D2 lines. This is the spectrum of hydrogen. When we fill the hydrogen in the tube and apply suitable voltage, we will get the spectrum of hydrogen. This is the spectrum of sodium. Here we will find D1, D2 lines at this particular point. If the resolution is higher, we will find these two lines separated more. Now, if the light is kept in a magnetic field, the magnetic field is produced by a coil like this, through which a current is made to pass. If the coil is broken or made to come like this, the one side will be north pole, another side will be south pole, and there will be magnetic field established, and the light produced will produce an effect called Zeeman effect, and the original line is split up into 3 or more components. This chart will show you the magnetic field produced by these magnets north and south, which I have already explained in the form of a coil like thing, and the light is kept in between these two, and the light that is coming out will be having polarized in a direction parallel if it is a straight line like this, and perpendicular if it is a dot like this. So, there will be parallel component and perpendicular components that are coming. In the center direction, when you look into it, we will find 3 lines. The central one is the original line, this side and that side are the lines due to the application of the magnetic field. If we introduce polarizer like at 3, the polarizer will cut off the central one, and we will produce only this side and that side, the effect of the magnetic field alone. Now, the spectrum we will be observing is, this part is without the magnetic field, the original lines as it is, and this part is the magnetic field, and the line is split up into these things, and this part is with the magnetic field as well as the polarides. This slide you are observing is that given by the original spectrum of Zeeman. It was produced in 1896 and it was interpreted by Lorentz, and there are two types of Zeeman effect. One is normal Zeeman effect, another one is anomalous Zeeman effect. This is the within the magnetic field. If you have the source is going to produce a spectrum, and if you have a facility to observe the spectrum in the horizontal direction as well as in the vertical direction. In the horizontal direction you will find only two lines, vertical direction you will find all the three lines. This is the normal Zeeman effect. The interaction of energy between the magnetic moment and the uniform magnetic field is given by this equation. This equation is delta E is equal to minus mu dot B, where B is this magnetic field applied in the z direction. Assuming that B is only in the z direction, we will have this equation will turn out to be like this. The interaction energy of the atom will be ml of the orbital magnetic quantum number in the equation, that is B will split the degeneracy of this into two or more states of the ml. Now, you find this ml splitting in the monitor, where ml the orbital magnetic quantum number. This equation implies that B splits the degeneracy into this. This is the original line with the magnetic field 0, that means without the magnetic field, and these are the lines which are produced because of the magnetic field. So, the effect of magnetic field is to remove the degeneracy and produce all these things separately. Normal Zeeman effect, the transitions that are observed are, here you will find the selection rules for Zeeman effect is delta ml is equal to 0 or plus or minus 1. That means 0 to 0 is delta ml 0, and 0 to 1 delta ml is minus 1. Like that you will find these transitions. There is only 3 transitions are valid. Hence, when B equal to some value, we will have 3 transitions allowed. Delta ml is equal to minus 1, delta ml equal to 0, delta ml equal to plus 1. So, the corresponding energy h nu is given by these 3 things. H nu 0 is the original amount of energy, that is the difference between these two energy levels, and that amount of energy is added here and subtracted here. Here the polarization effect is observed in such a way that the plus 1 transition of the delta ml is equal to this, we already know. The polarization is longitudinal in this direction sigma plus, and the transverse in this particular direction perpendicular to that. So, here 0, there is no polarization, only observed in the parallel, that is transverse direction. Minus 1 will give the polarization in perpendicular direction as well as longitudinal direction, and this is the direction of rotation of the electron and the magnetic field applied, and you will observe the polarization directions of this that is being shown. These are interpreted by Lorentz. Transverse Zeeman effect, where we will have delta ml equal to 0 or linearly polarized, delta ml is equal to plus or minus 1, the transitions are linearly polarized at right angles to the field. You are observing this particular slide that gives the two transitions 1D2 and 1F3, where L is equal to 2 and L equal to 3. This part is without the magnetic field. Now, when you apply magnetic field, there will be this particular thing is split up into so many as 7. This one is split up into so many as 5. Now, all the transitions are not possible according to the selection rules. Hence, we will observe one line here, one line here, one line here. So, using the selection rules, we will find these transitions are having the same amount of energy and they produce one line here. These set of transitions produce the central one, and this set of transitions produce the this side one. This is the polarized in this direction, and these two are polarized in the other direction. This is the extra term we are going to get using E b by 4 pi m. This is the normal Zeeman pattern. Now, this part of the figure shows the values for sodium D1 and D2 lines, and the lines are anomalous Zeeman effect. Here this is the magnetic field, without the magnetic field B equal to 0, and first lower level is 2s2 level, the upper levels are 2p half and 2p 3 by 2. The original spectrum consists of 5896 angstrom units and 5890 angstrom units. These two are the lines that are observed for sodium D1 and D2. Now, this is split up into 2 and this is split up into 4, and now all the transitions are available from here as well as here. So, there will be more number of lines than 3, and hence it is called anomalous Zeeman effect. The anomalous Zeeman effect that you are observing on the monitor is shown originally discovered by Thomas Preston in 1897. This occurs in atoms with non-zero spin and atoms with odd number of electrons, and it requires a what is called coupling between L and S. This coupling has been introduced by Lande in 1920, and he introduced the L value and S value are not separate, they should be added together to produce a J value. J is the total angular momentum, and hence the value will be J is equal to L plus S added vectorially, and this vector addition can be observed now. This is the arrow mark showing the direction of the magnetic field B, and you will find L as well as S two vectors, they should be added to produce J as a vector, and this J vector total angular momentum is rotating around the B value. Hence, this is how the atom experiences the magnetic field. The anomalous Zeeman effect produces the lines like this, D1 and D2 originally like that, and D1 becomes, there will be 4 lines and D2 will produce 6 lines, and like this more number of lines more than 3, that will be called as anomalous Zeeman effect. And in the case of hydrogen atom, it will be the normal Zeeman effect. In the case of sodium atom, this will be anomalous Zeeman effect. Both are compared with each other. Here normal triplet, and you will have the polarization directions, and corresponding, this is given by the model given by Sommerfeld, and these two will be like this in both the cases, and Dirac has introduced what is called spin. Hence, we will have the change from Sommerfeld to Dirac model will be like this. So, you will find hydrogen versus sodium atom being compared in this particular case. Anomalous Zeeman effect, when Sz is equal to 0, you will have Lz will be ml and h bar. Mu is equal to minus this g mu b by h bar into j, and the anomalous Zeeman effect is introduced on the basis of, these two are using the basis of quantum mechanics as well as wave mechanics. This one is based on the classical theory provided by Lorentz. Hence, here G is called Lande's splitting factor. You will find delta E, change in the energy, is given by this. Anomalous Zeeman effect spectra require this delta G, J is equal to 0 or plus or minus 1, that means change in the J value, delta Mj is equal to 0 or plus or minus 1, these are the selection rules, and hence polarization of these transitions we have already seen. We will observe this particular thing, this is the direction of the magnetic field, and J applied will be producing a vector being affected by that. So, we will have that j vector components are taken from this to this, it will be this one, this to this component on the z direction will be minus 3 by 2 plus 3 by 2, and this component will be plus 1 by 2, and in this component will be plus 3 by 2. These 4 components are shown in this particular part of the slide. This is, these 2 are shown in this direction, the other 2 are in the opposite direction. And you will have, without the magnetic field you will have this particular one, and with the magnetic field these 4 are shown like this. Change in these things are corresponding to the delta E, change in the energy. And now what we observe is this particular part of it is, the upper part is called mechanical moment, lower part is called magnetic moment. In the mechanical moment, the effect of the spin angular momentum and orbital angular momentum producing j total angular momentum. How the spin vector rotates and how the orbital vector rotates, and they both produce the j in the same way. Now, mu s, that is the magnetic moment, S magnetic moment and L magnetic moment, and they both together produce mu j, that is the total magnetic moment. So, the upper part is mechanical moment, lower part is magnetic moment. You observe a moving one, a dynamic one of this, you will be able to appreciate this. The lower one is the spin rotation, the upper one is the angular momentum rotation. Both these things put together, the red line will be total angular momentum, and total angular momentum will be rotating around the magnetic field that is being given. This will give us D1 line splittings and D2 line splittings and their corresponding polarization things. This is the polarization perpendicular and parallel, like that you will have in both the cases. What we have seen earlier is a ordinary spectrometer used in BSc and MSc labs. Now, what we are going to see in this particular monitor is the constant deviation spectrometer. Constant deviation spectrometer consists of a slit. From the source, the light passes through the slit, falls on it, and falls on what is called constant deviation prism. This is a very important thing, through which when it falls on, it will come out through the telescope, and here we have an additional facility of having a drum. This drum, when it is rotated, it will be calibrated in terms of the wavelengths. So, according to the wavelength that we are using, we will use this particular drum and take it to that particular thing. And apart from that, we require what is called a high resolution interferometer. You observe in this particular chart the Lumber-Gaitre interferometer. This interferometer is a simple plate attached to a simple right angled prism. The light ray enters into this and gets itself reflected several times, and in each reflection it will go there, and using a lens it is being caught on this particular focal plane, and we will get it as a spectrum of that. D is the thickness of this particular plate. In this one, you will observe in this chart the lines, original lines without the magnetic field, B equal to 0. So, we will find the distances from this to this and this to this, they are called L, and in this part we will find magnetic field is being applied. Once you apply magnetic field, there will be a splitting. The splitting is lower part and upper part. So, now you find from this middle part to the middle part is L, and after splitting from the splitted lower part to the middle part is L, or again from the middle part to the upper part, that is split again, is small l. So, like this we will have small l and capital L determined from the spectrum. This is the actual spectrum of the Zeeman effect. So, this Zeeman effect spectrum consists of the longer lines which are without the magnetic field, and the smaller lines on either side of the longer line are because of the magnetic field. This will be observed in the comparator to find out the distances between from the center of the longer line to the center of the shorter line on either side have to be determined, and the distance between longer line and longer line, if it is called as capital L, and distance between the longer line and the shorter line is called as a small l. Small l by capital L will give you some information regarding the calculations that I will speak a little later. Now, you observe in this part of the chart, first column is parent line reading. These are the readings that are taken on the comparator, and the between these two, if you take the difference, you will get this L. Similarly, between these two, this L, like that all these L values are taken. Now, the split line readings, this is upper one, this is the middle one, this is the lower one, like that these two are split lines. So, between the two split lines, what you observe here is called small l, and like that every time you will find small l. So, several L's are taken, several small l's are taken. What we do is calculate small l by capital L into this, and we will have all these small l, capital small l by capital L, and take the mean. So, this is the mean value. Now, you see this chart, we are finding a formula. This is the formula for finding out E by m of an electron. This is equal to small l by capital L and into 2 pi c square into root mu square minus 1 divided by b d, the brackets, mu square minus 1 minus lambda d mu by d lambda. Here L by L we have found out from the earlier chart table, and c is the value of the velocity of light, mu is the value of the refractive index of the glass plate, which is Lummer-Gerke plate, b is the value for this particular arrangement 6000 Gauss has been applied, d is the value of the thickness of the plate, which has been found to be 0.362 centimeters, mu square, and lambda has been found to be the 5870, and d mu by d lambda is the dispersive power of that particular one. Using all these things, we can calculate E by m. There are several applications of Zeeman effect. Zeeman effect is essentially that of the magnetic field. Wherever we have a magnetic field, we can use Zeeman effect. You can see the monitor, the sunspot magnetography. In the sun, there will be highly charged particles separately vigorously rotating, and they will be, when they are rotating, you will find them to be like this on the sun's photograph, and there will be very high magnetic fields. These fields are varying, and hence we can apply Zeeman effect here, and it is effectively a magnetography. And this is one of the modern instrument to detect Zeeman effect, and such things are available now in the market.
మా కార్యక్రమాలపై మీ సూచనలు, సలహాలు, అభిప్రాయాలు మాకు తెలియజేయండి. మీ సూచనలు, సలహాలు, అభిప్రాయాలు మాకు తెలియజేయవలసిన చిరునామా: డైరెక్టర్, ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామరెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500003.